So, number 4, weight is an excellent form of feedback on healthy behaviour. If we pay attention, once again, if we pay attention to the science and studies, the weight is an excellent measure from about 2 to 3 days out. So if I measure myself and I'm worried about just what I did last night and I measure myself today, maybe not so accurate. But across 2 to 3 days, it becomes pretty accurate. Across 7 days, it's really accurate. Across a month, extremely accurate. Across a year or your whole lifetime, what you weigh today has been largely dictated by what you do and what you've done across that time. There are other factors which we'll talk about, but your behaviour plays a huge part in where your weight goes. And the other reason it's obviously a brilliant piece of feedback is it's fast. You can do it anytime you want, basically. Like, everyone's got access to scales. It's highly repeatable and it's highly objective. Okay. Calories in versus calories out is true. We can't get away from the science. What makes it a little bit complicated is that there's a whole lot of factors that determine what calories go in. Not just how we feed ourselves, but also how we digest that and how we absorb that in our gut. But it still holds true. Calories out is affected by a very diverse range of factors as well, but it holds true. It's affected by our base metabolic rate. It's affected by our exercise. It's affected by our gender. It's affected by our muscle mass. But it still holds true. The maths holds up. And this is the formula for fat loss. So if you're ever looking for if you ever see the covers of magazines and they've got the secret to weight loss, unless they put that up there, they're wrong. So this is specifically for fat though, I must emphasise that. So that's what a fat molecule looks like. C55, H1O4, O6, so carbon, hydrogen and oxygen, put it in that combination, that's what fat looks like on average as a molecule. Obviously we can store it subcutaneously or viscerally, so under the skin or around the organs. And when we run the equation, when we combine that with oxygen, we end up with 55 carbon dioxide molecules. That's the breathing out we talked about before. And 52 water molecules. And it gives off some energy. So that's what happens when we metabolise fat. Now that blue arrow represents a very complex chain of chemical reactions within the body. But that's what you get every time that you break down a fat molecule. So 84% of that exits the lungs as carbon dioxide and 16% as H2O. So how do you think we create a body that produces more carbon dioxide and water and therefore breaks down more fat? Sorry, Patrick? Yeah. What can increase our breathing rate? What can increase how much energy our body demands? Here we go. So we need to build a system that optimises calories out. And that's where we come in. So these are the estimate equations that are used and universally accepted to be very accurate estimates of metabolic rate. So the Mifflin-St. Jeor, and I'm going to explain this as simply as I can. So the first part of that equation, with the 10m, that's mass. That's just your weight. The 6.25h, that's your height. The 5.0a, that's your age. S is a representative number of gender. So they use a factorial to change it according to gender. All right? Again, these are estimate equations, but they're highly accurate estimate equations. So according to Mifflin-St. Jeor, our mass, our height, our age and our gender, we can run that calculation and get a pretty accurate measure of how much energy we burn in a day at complete rest. That's what base metabolic rate is. So the only thing you can change if we use that equation is your mass. The other factors are not controllable. Another measure to estimate our base metabolic rate is the Katch-McArdle formula. So that's the 370 plus 21.6 times lean body mass. That's the one they use on athletes to get a good estimate. But we can use it on ourselves. And I like that one better because I like controllable measures. If I'm worried about this equation, well, I'm worrying about things I can't particularly control. This one, I can control how much lean body mass I have. And I can increase that lean body mass. And every time I increase that lean body mass, when I'm asleep, I burn more than the next person. When I'm exercising, I burn more than the next person doing the same amount of work. The average person requires this many kilojoules in a day. It's about 2,000 calories. But that's, if you run that equation and average out across Australia, it'll come out about here. All right? That's not base metabolic rate. That's if we just do our normal daily activities, maybe a little bit of exercise, whatever, 8,700. The great thing about the Harris-Benedict principle, and again, we apply that science, is we can multiply that by 1.25 by doing mild exercise on that day. So immediate payoff of 25% on the 8,700. We can run that 1.5 for moderate, 1.75 for fairly intense exercise, and very high intensity, we can bring that up to 2.0. So we can have a day where instead of only being able to consume 8,700 kilojoules, we can consume that much and we still weigh the same at the end of the day. That's what the exercise can do for you. But what also matters is if we can bump that up a little bit, what our body demands, then we're ahead anyway. So we also need to look at the quality and quantity of nutrition.